For this lesson, we're going to be continuing with our look at the tool set you need to put together in order to do curve sketching in calculus. A lot of the concepts we're going to be looking at here are going to be review, in the sense that we're looking at vertical and horizontal asymptotes, which is something we covered in the advanced functions course. The difference is going to be how we look at it. One of the new tools we've introduced with calculus is the idea of a limit, and so we'll be primarily focusing on that idea for today, not so much about derivatives as we are about limits. So when we talk about a vertical asymptote, any graph, so the graph of f of x, has a vertical asymptote at some location x equals c. This value c can be any value along the x-axis, if one of the following conditions is true. As we approach c from the left, so that means we're approaching c from values that are a little bit more negative than c, or a little bit more to the left of c. So if as we approach c, if that goes to plus or minus infinity, so as we approach c from the left, or if we approach c from the right, it goes towards plus or minus infinity. Now the easiest version of this, the trivial case, is just a rational function. So I've defined my f of x as p of x over q of x. This is going to have a vertical asymptote at x equals c if the quotient is equal to 0 when x is equal to c, and the numerator, sorry, I said the quotient, I meant the denominator, if the denominator is equal to c, is equal to 0 when x equals c, and if the numerator is non-zero. You might say, well, why does that matter? Because if I had 0 over 0, that would actually be a whole at x equals c. So it's actually important in this definition that the numerator is non-zero when the denominator is 0. That's for a vertical asymptote. Now, how does the graph behave around these asymptotes? And what do I mean? So this sheet, this blue page, is going to let me illustrate what these different limits mean. The limit as I approach c from below or from the left, the limit as I approach c from the left, the limit as I approach c from the right, the limit as I approach c from the right. And I've just put together 4 different sample graphs here. So the limit as I approach c from the left means I'm coming along this direction. It means here is c, this red dotted line represents x equals c, and I'm approaching it from a value to the left. So that's what it means when we say the limit as x approaches c from the left. Sometimes you'll hear me say as x approaches c from below. That means a value that's less than c. So in this case, as I approach from this side, it's saying that the limit goes to positive infinity. So that's saying that as I approach c from this side, as I get closer and closer to c, my curve is going to head towards positive infinity. Similarly, as x approaches c from the left, in this case if I go to negative infinity, that is going to look like that. And it's as simple as that when we talk about these limits. So if we find out the limit as x approaches c from below goes to positive infinity, that's what that part of the graph looks like. Keep all of this in mind in the context of what we're trying to do with this unit, which is develop tools to allow us to come up with fairly accurate sketches of what may be quite complicated functions. What happens when x approaches c from the right? Well, that means we're on the right-hand side of c. And so that means, and in this case it's going to positive infinity, so that means it's going to look something like this. And here I'm approaching c from the right, but I'm going to negative infinity, so it ends up looking like that. So, a more practical example, something you might encounter: determine any vertical asymptotes of this particular function, and then describe the behavior of the graph near the asymptotes, which is what I just did on the previous page. I was looking at the behavior near x equals c. Now, in order to do this, the first thing we're going to have to do is we're going to want to rewrite this in a factored form. Now, the numerator is just x, so I can't do anything more with that. The denominator, though, is a simple trinomial that can be factored into x minus 2, x plus 2, and x minus 1. Two numbers that multiply to negative 2 and add to positive 1. Now, this being the case, First thing we want to do is we look for any holes, which we don't have here. No common factors between the numerator and denominator. But from this, I can quite clearly see that x is not allowed to be negative 2, and x is not allowed to be positive 1. These are going to be my vertical asymptotes. And so I have a vertical asymptote at x equals negative 2, and I have a vertical asymptote at x is equal to positive 1. So the next thing we need to do is describe, we found the vertical asymptotes, we need to describe the behavior. And so what we're actually going to do when we talk about describing the behavior is we're going to look at the limit. In this case, we're going to take a look at the limit as x approaches negative 2, and we're going to do it from the left to start, of f of x. And that is the same as the limit as x approaches negative 2 from the left or from below of x over x plus 2 x minus 1. Now what we're going to do here is actually very much like the process we go through when we're doing an interval table. But I'm just going to go ahead and show you this in place. What we want to do, like an interval table, we're actually only really interested in the signs that are involved, positive or negative. So as x approaches negative 2 from the left, well, as x approaches negative 2, then x becomes a negative number. So this one becomes a negative number. As x approaches negative 2 from the left, so that would be, for example, negative 2.1, negative 2.1 plus 2, that one becomes a negative number. And as x approaches negative 2 from the left of this one becomes a negative number. So all three of these numbers are going to be negative. So that's the first thing we need to appreciate about this. Now the second thing we need to appreciate about this is that this is going to be a number like, it's going to be essentially negative 2. But what can you, and this number is going to be negative 2 minus 1. That's going to be negative 3. So right now we've just got a number over a number, but here what happens when x approaches negative 2 from the left? It becomes negative, but it also becomes a really small number. And then we've got negative 3 times a really small negative number. And so that's still going to be a really small number. And then we've got negative 2 over that really small number. And so what is the overall result? If I've got a negative over a negative over a negative, that overall is going to be negative. And then I've got a number over a really small number, that's going to be infinite. So the way this particular vertical asymptote works is the limit as x approaches negative 2 from the left of f of x is equal to negative infinity. And we're going to do the exact same thing from the right. So now we're going to say the limit as x approaches negative 2 from the right side of x over x plus 2 x minus 1. And as you get better with these things, you're going to be able to do them more quickly. So now let's take a look. As it approaches the negative 2 part, we know this is going to get closer to 0. But in this case, I'm going to be approaching it from the right-hand side. So that's going to be like negative 1.9. So this is going to become a positive small. That looks like positive smell, but trust me, it says positive small. This one is approaching negative 2, but negative 2 doesn't cause any problems here. So this one essentially is approaching negative 3. And up here, this one is approaching negative 2. And so you can see this time we've got a negative over a negative, which is going to become a positive. And I'm going to end up with essentially a number divided by a very small number, which is a really big number. So that's going to be positive infinity. Now it's actually going to be more useful. I'm not going to be able to deal with this here. I'm going to take this down. and I'll deal with it down here. So what happens with my vertical asymptote at x equals 1? So what I'm going to do is I'm going to take the limit as x approaches 1 from the left of x over x plus 2, x minus 1. Now you can do this in your head so long as you're careful about it, but I'm still going to, at the very least, I know that as x approaches 1, this is going to be a really small number. From the left, that's like negative 1.1. Negative 1.1, sorry, 1. No. From the left, that's going to be about 0.9. 0.9 minus 1 is going to be a negative small. And I'm just making up this notation. There's nothing special about this. I'm just using this to help me keep track. This number is approaching 1. That's just going to be 3, which is a positive 3. And up here, this is going to be a positive 1. And so when I work all of those out, you can see I've got a negative small and 2 positives, so that's going to be negative infinity. And then my limit as x approaches 1 from the right of x over x plus 2, x minus 1 is equal to, and now let's just go ahead and figure this out. We've got a positive number here, we've got a positive number here, and then something like 1.1 minus 1 is a positive small number, so we're going to approach positive infinity. And so there we go. We have our 4 behaviors, just like we did in these graphs, something very similar. You have to remember, your end goal of these things is going to be to graph them. And here is what that graph actually looks like. So you can see here are my 2 vertical asymptotes. From the left, I am approaching this asymptote towards negative infinity. From the right, I'm approaching towards positive infinity. From the left, I'm approaching this asymptote at 1 towards negative infinity. From the right, I'm approaching towards positive infinity. Sometimes these will be the same, so you can approach positive infinity on both sides or negative infinity on both sides. So in this case, it just happened to be that they were both flip-flopping. Okay, the other type of asymptote, again, something we're familiar with, but we're going to be looking at it from a different perspective, which is the idea of a limit. And that's a horizontal asymptote. Now, we've already talked about this kind of informally, which is the way a horizontal asymptote works is you imagine your x value going towards a really, really big positive number, which is like saying the limit as x approaches positive infinity, and a really big negative number, which is the same as saying the limit as x approaches negative infinity. If when you take these limits you end up with some value, so if you take the limit as towards positive infinity and you end up with a value L, well, that's a horizontal asymptote in the positive direction. Similarly, if you go towards negative infinity and you end up with some value L, then that's your horizontal asymptote in the negative direction. It's actually possible for these values to be different, but generally not going to be the case for any of the functions you're going to see. I just want you to be aware that if you do get different horizontal asymptotes, don't be completely freaked out by it. It can happen with some very specific functions. Now, how do I determine horizontal asymptotes? In advanced functions, you learned how to do that by long division. You learned a couple of shortcut methods, but because we're going to be trying to do this as a limit, we want to be able to express this in a way that allows us to evaluate the limit. So the easiest way to do it, and it's going to be easier for you to understand this when you see it, is I factor out the highest order variable from the numerator and denominator and then apply the limit. And of course, I'm going to show you what that looks like. A little note here as a warning, we have to consider whether the asymptote approaches the L value from above or below. And again, I'm going to illustrate that. That's something we really didn't pay a lot of attention to when we were graphing horizontal asymptotes in advanced functions. So this is another tool for the toolkit, but it also provides us with a more specific picture of what it looks like with the asymptote. Okay, so let's take a look at just some very general behavior. So here I've got my asymptote, and this is at the value, let's say, y equals L. So that's that value. And so let's take a look at these. The limit as x approaches negative infinity of f of x, it turns out to be approaching L, and this means from above. And that from above means from y values that are higher than L. So in other words, from above the asymptote. So that would be something that looks like that. That's how it would approach that asymptote. You can also get, I don't want you to think that's the only way this can work, you can actually also get something that looks like that. The end result is it approaches the asymptote from above, even though it may have crossed the asymptote at some other point. For now, we're just going to look at it in the simplest case. Whereas in this case, we've got the limit as x approaches negative infinity is approaching L from below. So that would be like that. Over here, the limit as x approaches positive infinity is L from above. So that's going to look like this. And the limit as x approaches positive infinity of f of x is equal to L, but we're approaching it from below, which is going to look like that. Same idea as the left and right, just a little bit different in execution. So as we did before, let's take a look and see if we can come up with the equation for any horizontal asymptotes. And actually, I didn't say here, although I meant to, because and behavior. If we don't include the behavior part, we're really not doing anything particularly new here. So now let me explain to you what I meant about finding horizontal asymptotes. The way I'm going to do this is I take a look and I see that my highest order term is order 2 as an x squared. So what I'm going to do is I'm going to factor x squared out of both the numerator and denominator. So what will that look like? Now it almost seems trivial to do it, but I'm going to do it here with the numerator. So I'm going to take out an x squared, leaving behind just a 3. In the denominator, I'm going to take out an x squared, leaving behind a 1 minus x over x squared minus 6 over x squared. And the reason why this works is if I multiplied it back out again, I would end up right back where I started. So notice I'm not factoring in the sense that I'm trying to factor this into binomial terms. I'm factoring out the highest order term. So from there, this simplifies to, now the first thing you might notice is, hey, x squared divides out with x squared, leaving a 1 and a 1. I'm going to address that in a second. Let me just go ahead and finish writing this out first of all, so you can see the final form. 1 minus x over x squared is just the same as 1 over x minus 6 over x squared. Now this is an interesting aside. I don't want to dwell on it for too long. But here I have divided out the x squareds from each other. Normally you would ask yourself, does that mean that x equals 0 is a whole? Is that what this is telling us? And the answer to that is no. Because if we look at x equals 0, we could actually, in the original function, we could have put x equals 0 in any time we wanted to. It wouldn't have been a problem. And the reason, the distinction between what I've done here and having a whole is that there was never a division by 0 in the first place. I have artificially introduced the division by 0. And it'd be no different than me saying if x is equal to 1, does that mean that x over x squared equals 1 over x squared? And now I'm dividing by x, so does this now suddenly mean that x is not allowed to be 0? Now, x was equal to 1, so x is not equal to 0. But the point is, I introduced this in my factoring process. So we haven't introduced a whole, and I don't want you to think that. And remember, the reason we're doing this is we're trying to identify the asymptote. So in order to find the horizontal asymptote, now that I've done this, I'm going to take the limit as x approaches, and I'm going to approach, well, let's start off with positive infinity of f of x, which is equal to the limit as x approaches positive infinity, which you can just write as infinity, of 3 over 1 minus 1 over x minus 6 over x squared. And so now when I do that, I'm going to go through that same process I did before, which is ask myself, okay, so what happens when I go to really, really big numbers? Well, 3 doesn't change. 3 just stays a 3. 1 doesn't change. 1 just stays a 1. But what happens to 1 over x? That becomes 1 over a really, really big number, which means this is going to turn into a 0. But what kind of 0 is this going to turn into? This is going to be, as it goes to positive infinity, this is going to be a really small positive number. So I'm subtracting a really small positive number, and this is going to go to 0 even faster because x squared is going to get big even faster. So what I end up with here is going to be a positive number over a positive number minus two really small numbers. Now, a positive number minus two really small numbers is still a positive number. And so what it turns out to be is, and if you take a look, this is almost 0, this is almost 0, so this is 3 over 1. So my answer is it's approaching 3, but it's going to be approaching 3 from, now I want you to think about that. Let me just put another note in here. So this is going to be a number that is just a little bit smaller than 1. It's going to be a number that approaches 1 from below. So it's going to be something like 0.99 or 0.999 or 0.9999. So that means that we are approaching 3 over a number a little bit smaller than 1 is going to be a number a little bit bigger than 3. So we're approaching 3 from above. There's a lot to unpack there. This is going to be one of those times where I'm going to specifically suggest you might want to rewind here and take a look at that again. Let's take a look at the limit going the other way, the limit as x approaches negative infinity of f of x, which is the limit as x approaches negative infinity of, and we ended up with 3 over 1 minus 1 over x minus 6 over x squared. So now let's ask ourselves, what's happening to the various pieces here? The 3 stays the same, the 1 stays the same. Now this is where things get a little bit more interesting because this approaches 0, but because this is to negative infinity, this turns into essentially a plus, right? It's minus a negative number. So this becomes plus a small number. And now this thing approaches 0, but because this is negative getting squared, this whole thing is actually a positive number. So this becomes minus an even smaller number. So we've got 1 plus a small number minus a smaller number. So adding a small and subtracting a smaller number means I'm adding a smaller number, doesn't it? And so this is 1 plus a smaller number, which means it's a number a little bit bigger than 1. 3 divided by a number a little bit bigger than 1 is pretty close to 3, but it's going to be approaching 3 from the bottom, like 2.99999. So there we go. We've got to the right, going to positive infinity, we're going to approach the asymptote from above. To the left, we're going to approach the asymptote from below. And I've got the graph of that right here. And you can see as we go to the right, I ignored vertical asymptotes here. They were there, but it wasn't the focus of what I was trying to do. As we go to the right, you can see we're approaching the asymptote, which is this red dotted line, y equals 3. We're approaching it from above. And then over here, you can see we actually passed under the asymptote, and then we came back up, and we approached it from below. And that is it for this lesson. This lesson was brought to you from my lab at the school. So if the sound is crappy, I apologize for that because I'm not using my regular headset. And if it's noisy, it's because the fans are on here in the school. That's it, and good luck with your continued curve sketching.